Good morning. I think that we can take the seat. I'm sure that there are more people coming through. But let me welcome you, and then please take a seat at the back. My name is Xiaohua Xia. It gives me great pleasure to chair this plenary session. I'm going to do a very, very brief introduction to Professor Lei Guo. Professor Lei Guo was born in 1961 in Shandong province, and he got his BS degree in mathematics from Shandong University in 1982 when he was 21. If you don't know where Shandong province is, it was where Confucius was born. And in 1987, when he was 26, he got his PhD in control theory from the Chinese Academy of Science. And then in 1991, when he was 30, he became the AE, Associate Editor for Siam Journal of Control and Optimization. In 1992, when he was 31, he became a full professor of the Institute of System Science of Chinese Academy of Science. And then there are quite a few highlights, but then I want to emphasize the highlights when Professor Lei Guo was associated with Ifac. In 1993, when he was 32, he won the Young Author Prize from the Ifac World Congress in Sydney. I think this is one of his first associations with Ifac. And then in 1998, when he was 37, he became IEEE Fellow. 1999, when he was 38, and then he offered his first Ifac World Congress plenary when in Beijing. When he was 40 in 2001, and he became the member of the Chinese Academy of Science. If you know the Chinese politics and the academic environment, you know what that means. And then in 2002, when he was 41, he became the fellow of the Third World Academy of Science. I just select a few just to talk about. When he was 32 in 2003, he became the president of the Academy of Mathematics and System Science, Chinese Academy of Science. And then his third association with Ifac in 2005, when he was 44, he became the council member of Ifac, representing himself and largely the Chinese NMO. In 2007, when he was 46, he became the foreign member of the Royal Swedish Academy of Engineering, and he became the Ifac Fellow. So his fourth association with Ifac. In 2011, when he was 50, he became the advisor of the National Basic Research Program of China, which is a very, very high-profile position in the Chinese academic system. Now, he is the director of the National Center for Mathematics and Interdisciplinary Science, Chinese Academy of Science, and he's also the current president of Chinese Society of Industrial and Applied Mathematics. And now, he's only 53, he's giving a second plenary speech at the Ifac World Congress. Let's welcome Professor Lei Guo.
Thanks, Xiaohua, for the kind introduction. Ladies and gentlemen, it's a really great pleasure and honor for me to be invited to give this lecture at the World Congress of Ifac. So for this, I would like to first thank the Ifac president and the organizers for the invitation. As you can see from the title of my talk, I'm going to present some results concerning the fundamental limitations and the maximum capability of the feedback mechanism, which were conducted over the past 10 years with my colleagues. So now let's first have some background. So as we all know, feedback is ubiquitous, and its feedback is needed in almost all purposive behaviors. And you all know that feedback is a fundamental systems principle, and also a core concept in automatic control. So it is a feedback concept together with the feedback theory that distinguishes our field of automatic control from any other branches of science and technology. So you all know that the main reason for using feedback in control is that uncertainties always exist in modeling, identification, and controlling and running of practical systems. And uncertainties usually contains two parts. I think two classes. One class is we call the internal uncertainty, another is external uncertainty. By internal uncertainty, we mean the uncertainties in the system structure and the parameters. By external uncertainty are usually treated as disturbances. So it is for this reason the feedback control of uncertain dynamical systems has been a central theme in control theory, and I would like to see tremendous progress has been made. For example, in the field, as you all know, robust control, adaptive control, nonlinear control, and stochastic control. And together with this, and here is a list of the typical techniques that developed over the years. I just name a few. For example, the PID control and the internal model principle, and the sliding mode control, and absolute stability together with the Popov criteria, H-infinity control, self-tuning regulators, model reference control, small gain theorem, and the backstepping method, and the active disturbance rejection control, and it's called ADRC. So just to name a few. And so we all know that any theory needs assumptions, and any mathematical models are simplifications or approximations of the real system. So just like Albert Einstein said, we should make everything as simple as possible, but not simpler. So I would like to say, while it may be necessary to have a theory established for simplified models, one may naturally expect that a theory can give the boundaries of its applicability to real systems, which are mostly nonlinear and with uncertainties and different from our model. Okay, here are some challenges for the feedback theory. First, the implementation of control. As we know, feedback cannot be implemented instantaneously in general due to sensing, sampling, communication, computation, actuation, and so on. So this turned out to be quite challenging in theory, actually. The second issue concerning identification for control. You may ask, is identification really necessary for control? Furthermore, how much uncertainty should at least be reduced by modeling and identification in order that the remaining uncertainty can be effectively dealt with by feedback? Concerning model-based control, you may ask, can we see anything about the maximal nonlinear uncertainty that can be dealt with by controllers that are designed based on a given model class? For data-based control, you may want to know, do we know any limitations of the controllers that are designed on the basis of the online observed or measured data? So for adaptive control, many of you may know that there is a relatively complete theory for adaptive control for linear systems. And that theory can be generalized to a class of nonlinear systems where the nonlinearities have a linear growth rate. So a natural question is, can we design a globally stabilizing adaptive controller for discrete time uncertain systems with nonlinearities having a growth rate faster than linear? If you cannot, is it due to our personal incapability or due to fundamental limitations of feedback? Concerning hybrid nonlinear control, we consider a typical case where we have a continuous time dynamics controlled by sample data feedback. So you may ask, can we have some concrete results on sample data control of nonlinear uncertain systems when the sampling rate is prescribed? That is, it cannot be arbitrarily small, as small as you want in theory, as a given one. So all these questions really related to the following problems. First, how much uncertainty can the feedback mechanism deal with? And then what are the limitations of the feedback mechanism? And how to construct the most powerful feedback law? And how does uncertainty affect the feedback performance? So you certainly natural, I think that there are many related directions to such problems. So I would like to see much progress has been made in control theory, especially in such areas like robust control, adaptive control, and so on. However, I would like to see that few results really address the maximum capability and the limitations of the feedback mechanism. I will define what is the feedback mechanism shortly. It simply contains all the possible feedback laws with no restrictions on the construction. Now let's have a little more detailed look at robust control. Normally, in robust control, we have a nominal model plus uncertainty, usually described by a ball. And so this is a typical diagram in robust control, infinite control, H-infinite control. So the controller law design based on the nominal model and usually from a given class of as a feedback class. And I would like to particularly emphasize that in robust control, the measurements are not used to reduce the uncertainty ball. That's so I would like to see the robust control is related, but essentially different from our problems that raised a few minutes before, in both problem formulation and the results and the results we get. Next, we consider another big field, adaptive control. Here is a typical diagram situation for the adaptive control. We have uncertain systems and with the adaptive estimation, estimating either the structure or the parameters, and then construct the controller. So a typical design method includes the Venn certainty equivalence principle and the Lyapunov function-based design. So I would like to say that in adaptive control, the adaptive control usually does not address the maximum capability and limitations of the adaptive feedback. So let's now have a look at our problem formulation. First, we have a dynamical system. And with input sequence denoted by UT and output sequence denoted by YT. And the information, we have a prior information or prior knowledge about the system, I0, and IT is posterior knowledge about the plant. So, and that's the observations, Y0, Y1, YT up to time t. It is the posterior information that enables us to reduce uncertainties of the system to be controlled. So here is a definition of our feedback. Because we would like to investigate the maximum capability and the fundamental limitation of the feedback, we have to give a definition, precise definition for feedback. First, a feedback signal, UT is defined like follows. There is a measurable mapping from the data space to the input system. For simplicity, we take the single input case. We consider single input case. So FT can be any nonlinear transformation, certainly include linear, nonlinear, time-varying, any kind of transformations, and constructed based on observation data. Then we call it a feedback signal. The feedback law is a collection of the feedback signals, and the feedback mechanism is a collection of feedback laws. So from this definition, you can see that we lose nothing by such defined feedback mechanism. So whatever method used in designing the feedback, it can be written in this general form, like this, depending on the data. Okay. So before going further, I would like to say something about a description of the uncertainty. Uncertainty is mathematically described by a set, all of you know, either parametric or functional. And the control of uncertain systems is, by definition, the control of all possible systems corresponding to this set. Okay, that's I suppose everybody knows. I should emphasize that here. Okay, now let's have a brief look of the conceptual problem formulation. Here we have a dynamical system, and with uncertainty f belongs to a class, either parametric or functional or non-parametric, and then we have a feedback law. You taken from the feedback mechanism contain all the possible feedback laws that you can construct. Then we would like to consider the so-called BI/BO stability and the boundedness. Global stability, so for any initial condition, and the output depends on F and U, certainly. And we would like to have such a output at least bounded for all T. And this hold for all F belong to this uncertainty set. And we would like to minimize, because we would like to consider the BI/BO stability. And then the size, we have a size of the uncertainty, which takes the supreme of the size, F, the size. Then this is a this can be used to describe our feedback capability. Quite complicated, but quite natural also. So concerning this, then we may ask the following questions: how to properly define the uncertainty set, and how to characterize the limits of the feedback, and how to construct the most powerful feedback, and how to analyze such dynamical systems. I would like to say that even if a nonlinear feedback law works well both numerically and practically, the last question, that means how to analyze such dynamic systems, may still not be easy in general, just like the well-known case of self-tuning regulators. That's the least squares estimation used to construct the feedback law for linear stochastic systems. Okay, before going further, I would like to show you a very simple and actually trivial fact, a basic fact, concerning about impossibility. Let us assume that F0 and F be two class of uncertain systems satisfying and that F0 is a subset of F. If the system class F0 cannot be stabilized by the feedback mechanism, then neither for the larger class F. That's very trivial. However, usually when we when we have a theorem, theoretical theorem, and normally we would like to have the conditions or systems as large as possible. The conditions as weak as possible, system as large as possible. That's for possibility theorem. However, for impossibility theorems, the system class is a basic, simple, is better. Because if you cannot control a subclass, then you cannot control the larger class. That's a trivial fact. So that's why we focus on some basic class of uncertain system later on. Okay. So concerning impossibility theorems, here we have some well-known impossibility theorems in the literature in science. We all know the body integral theorems on sensitivity function, and the channel coding theorems, also Cromie-Rolle bound in statistics. I will back to Cromie-Rolle bound later on. And Heisenberg uncertainty principle in physics, and Gold incomplete theorem in mathematics, even error impossibilities in economics. So in a similar spirit, here we try to understand the feedback capability, impossibility theorems, pursuing the fundamental limitations and the maximum capability of the feedback mechanism. Why we need to do that? Why we care about such kind of results? Well, what I can see is that fundamental limitations can prevent us from wasting time and energy on searching for an expected feedback controller that does not exist, and alert us of the danger of being unable to control uncertain systems when the size of uncertainty reaches the limit established. Also, we demonstrate the necessity for a better modeling and identification. If we can establish some limitations for feedback. The maximum capability can encourage us in improving controller design to reach or approximate the maximum capability that we know, that we established. And may also guide and help us in relaxing the task and effort in mathematical modeling and system identification. I will back to this issue, back to the modeling and feedback and later on. So let's start with the following basic model class. Here, Y and U the sequence are output and the input sequences. W is any bounded disturbance or white noise. Okay. And F belongs to a class F with uncertainty. So you can ask how much uncertainty in F can be dealt with by feedback. Before going further, I would like to say something about uncertainty as a nonlinearity. So we distinguished parametric case from the non-parametric case. The parametric case means the uncertainty can be described by a finite number of unknown parameters. It is a nonlinearly parametric, that the theta is within the function f, or linearly parametric case is outside the function case. The non-parametric case, that means it cannot be described by a finite number. And instead, an infinite number of unknown parameters. We call this case a non-parametric case or functional uncertainty. By nonlinearity, I will use a denotation throughout the talk. That means f equals capital theta x to the power b, which means there exist two positive constants, C1, C2, such that this inequality holds for sufficiently large x. Certainly, this condition can be relaxed when we only consider impossibility or only consider the possibility results. Okay. Okay. another thing I would like to emphasize is a sensitivity function, denoted by the derivative with respect to the unknown parameters. So it's interesting to note that if the change of a state has no significant influence on function f, then there is probably no need to care about it. Although it's maybe very large range. In fact, the growth rate of the sensitivity function is more relevant than the range of the parameter change. And the following quantity will play a key role. That really is correctly describes the growth of the sensitivity function. So now let's have a look at some fundamental theorems concerning the feedback mechanism. So we will consider three cases. First case is a parametric case, where uncertainty can be described by a finite number of unknown parameters. The second case is a non-parametric case. I mean, uncertainty is a function, not a parameter, and that means the system structure is unknown to us. The third case concerning about the sample data control case. Now let's start with first case polynomial criteria. Here is the first result I would like to show you. The critical case, the critical value b equals to 4. Let us consider this basic control system with uncertain parameter theta in the nonlinear function f. Assume that the sensitivity function has a following growth rate x to the power b, where the unknown parameter theta lies in a compact set, and the UT is any bounded sequence or white noise. So this theorem says that the growth exponent b equals 4 is critical. Means that the bulk class of systems, uncertain systems, is globally stabilizable by feedback mechanism if and only if b less than 4. This theorem says that if b is less than 4, we can definitely construct a feedback law such that the system, the uncertain system, is globally stabilized. On the other hand, if b is greater than or equal to 4, then the system cannot be globally stabilized for any feedback laws. Here we have a simple corollary. In the case where theta is outside of the nonlinear function, as again, the sensitivity function looks like f as to the power b and the growth. I would like to mention that when b is less than or equal to 1, that's bounded by linear growth. We have a relatively complex theory for that, even for general systems. Again, b is a critical. B equals 4 is critical, and then the bulk class of systems, uncertain system, is globally stabilizable by feedback if and only if b less than 4. From the problem formulation, it's really hard to see why b equals 4 is a critical value. So here is I'm trying to explain that, and then from our analysis. But intuitively, why b is 4, I don't know. So first, I would like to say the noise effect is essential. Because if there were no noise, if there were no noise, we can solve the unknown parameter with one step, okay? Then after that, the control problem, the stabilization problem is trivial, regardless of the value of b. For any b, you can stabilize the system because you can solve the unknown parameter within one step if there is no noise. However, in the noise case, and let us assume that for simplicity is a white noise, or even Gaussian white noise. And f yt is simply yt to the power b. Then the best, in some sense, least squares estimator is the best estimator in some sense. will give a natural feedback, certainty equivalence feedback. And so we will have a closed loop system like this. And note that the estimation error will decrease at a rate roughly about this, as long as the sequence increases fast enough. So this term will increase. Okay, this term will decrease. So it turns out that the critical case for stability is b equals 4. But sure, you should give a rigorous mathematical analysis. Yes, we can do that in this way. The rigorous analysis for the general case hinges on the following inequality. For any positive sequence satisfying this inequality recursion also, then ST is bounded, provided that b less than 4. So if for any sequence satisfying this inequality ask for boundedness, then that's also a necessary and sufficient condition. Okay, this condition related to the following polynomial criteria. So related to this second order polynomial is positive for this in this interval, then if and only if b less than 4. So let us consider slightly more complicated case where we have additional uncertainty in the input channel. So besides unknown parameter theta 1, we have another parameter theta 2. And so theta 1, theta 2 belongs to a compact set with this one does not equal to 0, and any bounded noise. Also, again, we assume f has such a growth rate, a sensitivity function. And this theorem says that the uncertain system, undynamic system is globally stabilizable by the feedback mechanism if and only if b less than 3. Reduced when we have additional uncertainty in the input channel, and the feedback capability reduced from the original b equals 4 to the currently b equals 3. So certainly you can have generalizations where you have multiple parameters and the p-dimensional unknown parameters, and again, the bounded noise or what noise. Again, this is a vector, and the components like this, we assume that each component has such a growth rate, and without the loss of generality, we put all the BIs together, and we assume without loss of generality that B1 greater than B2 and arranged in a decreasing order. And then we can use this exponent to define a polynomial. That's why we call it a polynomial criteria. So how we use this to define a polynomial like this? With the exponents bi introduced above, define the characteristic polynomial like this. In the general case, p-dimensional unknown parameters. Sorry. This theorem says well, any f belong to fb, a nonlinear function, then the above uncertain nonlinear dynamical system with theta belong to this compact set is globally stabilizable by the feedback mechanism if and only if this polynomial is positive for any z belong to this interval. So we transformed the feedback capability from the growth rate exponent to a polynomial. So that's why we call it a polynomial criteria for the maximum capability with the feedback. Okay, certainly you can have a series of corollaries. So, for example, consider the simple polynomial regression case. And so by the polynomial criteria we just mentioned before, using this theorem, so you can get the following results. For any BI with B1, as long as B1 greater than or equal to 4, the system is not globally stabilizable. So 4 is a critical value. This is a necessary condition. And for any BI with summation of BI less than 4, then the system is globally stabilizable. So furthermore, for any B1 greater than 1, there always exists a dimension P together with the exponent bi, such that the corresponding system is not globally stabilizable. So this really means that the class of uncertain non-parametric functions with growth rate faster than linear is not globally stabilizable. Now we are back to this issue later on. Even in the second part, we will see that even for linear growth case, there are some limitations. Okay, now let's have a look at a general case where we have a non-linearly parameterized case. The unknown parameter is inside the function f. Okay, again, it's a p-dimensional unknown parameters. The bounded noise belong to this class with a sensitivity function satisfying this. Each component of the sensitivity function satisfies this growth rate. Okay, sensitivity function. Again, we denote B as the collection of B1, BP, the growth rate of the sensitivity function. Using this, consider again the following characteristics polynomial defined as the same as before. And we introduce a set omega is a set of B satisfying this one. Another two sets of B. One is a polynomial positive. And this one is a B1 greater than 4, the polynomial. So this omega, omega S, omega U are all sets of B. So it can be shown that this is a subset of this. And furthermore, you can show that the above class of uncertain nonlinear system is globally stabilizable by the feedback mechanism, provided that B belongs to this set. And the above class of uncertain nonlinear systems is not globally stabilizable by the feedback mechanism as long as B belongs to this set. So now let's us take any set of B such that is in the middle of this one. Then we have a following quite abstract theorem. Looks like this. Consider uncertain class if f belongs to this interval, then the function class can be decomposed as a union for this f r of b, where f r of b are disjoint and non-empty families of functions for different alpha, such that for each function belong to this subclass, the corresponding system is stabilizable by feedback if and only if the parent B belongs to this set. So now we really established the one-to-one correspondence between the parameter set and the function set. So next, I will briefly mention the rationale and the ideas behind the impossibility. Why we have an impossibility theorem? Why we have some fundamental limitations for the feedback mechanism? Just some intuitive explanations. Let us assume that sit the random vector independent of the disturbance, and consider this system phi depends on the past input and output data, and W is a white noise with variance sigma W square. And let's denote F hand as a conditional expectation given the observations, observation sigma algebra. Okay, then so by simple manipulations you can have such a equality. So the problem is how to get a universal. Means independent, and of the input or hold for all input, for all feedback laws, are universal and valuable lower bound. So a trivial lower bound is 0, so it's not valuable for us. Okay. So one can see maybe this kind of problem related to the Karami lower bound, as I mentioned before. So we have a standard conditional Karami inequality that gives a lower bound to the covariance, conditional covariance of the estimation, of the best estimation actually. And so the problem here is that how to estimate the Fisher information matrix. If you cannot estimate properly, get good estimates, then there is no way to get some useful analysis leading to the impossibility theorem. And another big question is how to realize about idea in a deterministic setting. As I said before, theta belongs to a compact set. The noise is any bounded disturbances. So that's a deterministic setting. How to realize this, the random idea in a deterministic setting is a problem. So now we use a stochastic embedding. So starting from a deterministic framework, where the parameters in a compact set and the noise is any bounded noise, we embed the stochastic distribution on that and get a stochastic framework. Within the stochastic framework, we can use a conditional Karami rule like a bound to get some useful lower bound. And we can find a set D with positive probability, then such that the impossibility theorem hold. Then we can take any point in this set D, then back to the deterministic framework. So that's our idea. So I would like to remark that the stochastic embedding idea or approach may not be effective, may not be that useful when you establish the possibility results. So as I said, I'm explaining how to establish the impossibility results. Okay, when we try to establish the possibility results, so it's not effective due to the well-known exceptional set problem. You have a set of probability 0 that may contains your real parameters. So for establishing the possibility part, we have to use other method. But I'm just talking about the impossibility part. Okay, the parameter distribution embedding, we take set, sorry. Okay, we take set to have the following spherical probability density function like this. Okay, and we take the noise sequence have such a decaying Gaussian distribution like this. So within with above stochastic embedding, the Fisher information matrix can be calculated and leading to a useful lower bound. And P is defined like this. So this is a key step in establishing the impossibility theorem, and followed by a meticulous analysis of the involved nonlinear dynamical inequalities. And finally, you can arrive at a connection with the polynomial criteria. Then the long and tedious analysis. But anyway, that's a key idea. So let us consider the second case, critical value 3 over 2 plus square root of 2. Let us consider the non-parametric case where the uncertainty of the system is a structural uncertainty or described by a function set. So let us consider following basic class. With unknown function f, for simplicity, we assume it's R1 to R1 mapping. And we introduce a Lipschitz norm, is actually semi-norm, like this. The norm of f defined in this way is actually the smallest Lipschitz constant, right? So this norm is the Lipschitz constant, the smallest Lipschitz constant for this function f. With this norm, you can define a ball in this functional space like this. Okay, for any f belong to this function, and with a norm less than L, we define f L. So L can be is really the radius of this ball in the function space. It's obvious that the larger the value L, the larger the uncertainty function is. So L can serve as a measure of the uncertainty, the size of the uncertainty, okay? Okay, so let us consider a case for open loop control. If we delete the feedback, UT, then we will have a nonlinear dynamical system like this. Okay, if we want, if this dynamical system is bounded, BIBO sense, then you can use a small gain theorem. And you can say that a necessary and sufficient condition for the stability of the open loop case is that FL, for stability for this class, is that L less than 1. That's a contraction map. Right? That's the best you can do. That's a necessary sufficient condition in the open loop case is L less than 1. So a natural question is, when we use feedback, is L less than 1 still the critical case? Or can we push L from 1 to arbitrary number? So answer is no. So these are the contents of the following theorem. This theorem says the above class of uncertain dynamical systems described by the family of uncertain sets, the FL, is globally stabilizable by the feedback mechanism if and only if L less than 3 over 2 plus square root of 2 is a near 3, 2.9 something. So that's the best you can do with feedback. However, anyway, as I said, with feedback, we have pushed the L from 1 to this number. So this theorem means that if L less than this number, then there is a feedback law such that the system is globally stabilizable for any F belong to this set. On the other hand, if L is greater than or equal to this number, then for any feedback law, there is at least one system in the uncertainty set such that the corresponding closed loop is unstable. So that's the precise meaning of this one. Now let's have a look of a brief explanation from our analysis why this is critical. Let us consider YT be any sequence satisfying this inequality. That's a very interesting inequality. And so for a given sequence, YT, not necessarily generated from our control system, arbitrary sequence. Okay, let's assume that this sequence satisfies this inequality, where the center is defined like this: the minimum value plus maximum value divided by 2, and the neighbor is defined as the nearest point to YT from Y0 to YT plus minus 1. So it's a neighbor, it's a center. If YT plus 1 subtracted by the center and the absolute value less than L times this number, then it follows that if we ask for boundedness for any such sequence, then if and only if L less than this number, 3 over 2 plus square root of 2. That's quite interesting. Another related fact with this number is as follows. All solutions of this linear equation either converge to 0 or oscillate about 0 if and only if L less than this number. These two facts are all related to our analysis in the proof of this number. So now let's have a general theorem. Let G set be a model class with modeling error or non-parametric modeling error. A parametric model class, okay, C belongs to this interval, and F belongs to this interval, this set as defined as before. plus a bounded disturbance like this. So we have a model structure, parametric one. Nonlinear function G is known, theta is unknown. Phi is a regression vector, a general regression vector. And F is an uncertainty, and non-parametric uncertainty, a functional uncertainty, plus a bounded noise. We assume that the system, a nonlinear system, satisfies a certain kind of minimum phase condition, and that the sensitivity function of G is bounded by the linear growth. So certainly that includes a linear model. It can be neural network, fuzzy network approximations, and the like, any parametric model. So this theorem says that about uncertain system with F belong to this capital theta and F belong to this set is globally stabilizable by the feedback mechanism if and only if, again, you have this critical number. Okay, now let's look at this problem from the robust control point of view. Okay, let us assume that G is known, theta is known as a nominal model. Okay, is a nominal model class. These are uncertainties. Okay, within the robust control framework, I think the best you can get is that L less than 1. As I said before, by using the nonlinear small gain theorem, treat F as an uncertain function. Okay, because in that framework, there is no intention to try to estimate the uncertainties using the observed data. Okay, that's designed based on the nominal model. Okay, here is both theta and F is unknown. Okay, we have such a general theorem. Okay, now let's let G be a real uncertain system, and G be a model class parameterized by this one, theta, and G is no structure, and we can rewrite G as two terms. Okay, G here is nominal part, and the model part, and the uncertainty part like this one. So as we all know, modeling and feedback are two main techniques in dealing with uncertainties. And about theorem, we just stated, and essentially quantitatively shows how modeling and feedback are complementary in control system design. And in particular, the limitations of feedback may be compensated by improving the quality of modeling by either understanding more about the concrete system mechanism or choosing a more powerful or more suitable parametric structure, or by both. Okay, now let's have a look at the third case and the sample data feedback. We also start with a simplest case, but non-trivial case. Consider a continuous time nonlinear control system like this. And again, where is the state and the U is the input. You can plus noise or not. That doesn't matter because F is an uncertain function. It's a local ellipse. It's a standard assumption. So the sample data feedback with sampling period H is defined simply by the zero-threshold function like this. Again, GK may be any function. Okay, linear, nonlinear, the time varying or linear transformation from the observations to the input space. Yeah, as I said, it can be any measurable functions. So before presenting our impossibility theorem, let's have a look at two simple examples. One simple example concerning about what happens for a stabilizing feedback under sampling. Let's be a scalar unknown parameter in this system, and the G is a local ellipse and has upper bound like this. And it's easy to show that the continuous time feedback is globally stabilizing. It's easy to prove that. But the corresponding sample data feedback, and when you change yt to ykt, when yt here, ykt, and like this, is not globally stabilizing, no matter how small the sampling period is. So another example, this example only concerns a specific feedback, okay, a specific feedback, and does not say anything about other feedback. The next example shows the limitations of all the class of sample data feedbacks, like this. Feedback capability on the sampling. Again, we consider a simple system. We have the stochastic differential equation described by stochastic differential equation, local ellipse, and the standard Brownian motion or Wiener process. Assume that f is a growth, the growth rate of f is faster than linear in this way. Then the stochastic system is not stabilizable by any sampled data feedback. And in fact, for any capital T, this system will explode. For any initial condition and any sampled data feedback, whenever how small the sampling period h is, even if f is known a priori. So it's very simple. When f is known, you can cancel this and introduce a linear term. Then it's stabilizable. So this shows what happens for the feedback mechanism when we have sampling. So the key point is even for very small, arbitrarily small h, the global stabilizability is still not kept. So from these two examples, we see that maybe one key point is your nonlinear function has a growth rate which is faster than linear. So how about the case where the nonlinear function have a linear growth rate? So in this case, many of you may know that as long as the sampling period is small enough or the sampling rate is high, sufficiently high, then it's okay. But the question is, how about the case when h is not allowed to be arbitrarily small? That means a given or prescribed sampling period. Here is a partial answer of this problem. Consider again the basic control system with a local ellipse function belonging to a linear bounded class. L is the slope of the function. This theorem says up to now we have no restrictions on the sampling period h. If sampling period h times a slope greater than this number, then the uncertain system class and with linearly bounded function cannot be globally stabilized by any sampled data feedback. That gives the other impossibility theorem. Certainly, as said before, when h is sufficiently small, then that's okay with linear bounded. But the thing is h is a given one, and therefore arbitrary given. So that gives us an impossibility theorem for for the feedback. Okay. Now let's have concluding remarks. So first of all, I would like to mention that all the impossibility theorems presented in this talk enjoy universality, in the sense that they are actually valid for any larger class of uncertain system, as I mentioned before, and for any feedback laws that you can construct. And the main results also indicate that the feedback capability depends on both the information uncertainty and the structural complexity, although our focus here is mainly placed on the information uncertainty. And we also have noticed that sensitivity function is more relevant than the range of unknown parameters. Third, as we have observed, there are fundamental differences between continuous time and discrete time or sample data feedbacks for uncertain nonlinear systems in both the results and the analysis, where time lag in feedback is an inevitable feature for our problem for the later. And of course, various generalizations of the results are possible. In particular, time delay and time varying system may also be investigated. Finally, I would like to see the investigation of the maximum feedback capability appears to be practically valuable, theoretically fundamental, and mathematically challenging. So this lecture only actually presents some preliminary results, and there is still a long way to go towards a complete understanding of the fundamental limitations and maximum capability of the feedback mechanism. So here is some about 10 related publications. For those who are interested in the details of the results, can look at the paper. Okay, finally, acknowledgements. I would first like to acknowledge my collaborators over the past 10 years. Most of them are my former graduate students. I would like to particularly mention, Liang Xie, Feng Xue, Chan Yingli, and Chao Donghuang, and for the contribution to this series of work. Over the years, I've also benefited much from discussions with many colleagues around the world. And I would also like to use this opportunity to thank them all. Some of them may sit in the audience in the room. And I will also like use this opportunity to thank the funding agencies in China, particularly the National Science Foundation of China, for the long-term support. Finally, I would like to thank you all for your attention. Thank you.
Yeah, thank you, Lei. I think it's for the excellent presentation. We, as control guys, that we talk about possibilities and endless possibilities, and I think it is so inspirational to know that we have also limitations, boundaries, impossibilities. So for that, I think the result is inspirational and so fundamental, and for that we thank you. I know that you will have questions, and then you will have your doubt, you want the challenge, but as we said, this is the plenary. I know there's even a special audience, my wife, she's trained as a mathematician, so she's never been to a control speech, so it's her first time. I know that she's got a lot of questions. I won't give her a chance, so I won't give you a chance. So I think let's just conclude by put our hands together for an excellent speech by Professor Lei Guo. Thank you so much.